what I want to talk about starting today and continuing next week is, all right, let's do the opposite now. How about if we say, not steady state. Let's look at transients. But I still want to play in a kind of a safe corner, so I'm going to say, let's forget about steady state. Let's calculate the transient, but let's forget about the gradients and assume that the temperature is constant. All right? So if I say the temperature is constant, and I have, say, a sphere that is cooling down, what is the difference in temperature between the center and the surface? It better be, right? We know that in reality it's never going to be exactly 0. But engineering is the art of the good lie, right? It's going to be 0 for all practical purposes, right? So I'm starting by saying the temperature is homogeneous, acknowledging that in reality what we mean is there is a slight variation of temperature, which we will study later. But right now, when we talk about the surface, we talk about the center, we talk about the 3/4, we talk about a crazy shape. Anywhere in that shape is going to be same temperature. Are we all on the same page with that? Okay, so if for the sake of what we are talking about here, let's say, I haven't even told you what I'm going to be talking about, but we have a cylinder now. What is the temperature profile inside the wall of this cylinder? Somebody says 0, but the answer is constant, right? Right? And when I calculate convection, it's going to be, right, in convection we always use TS because it's a surface temperature. In the case of the wall, we calculated all that because it was not the same. But now I'm going to call it just T. Of course, it has to be TS, but TS and this temperature in the middle are all the same now for us. Okay? So this methodology, or this big lie that is so incredibly convenient, is called, in the book is section 5.1, and leave a room here for the bigger title, I'll give you in a second. It's called the lumped capacitance method. Right? And this is part of, in the book is section 5, transient heat conduction. Right? This is the section, the big section, the chapter in the book, lumped capacitance method. All right, so in the lumped capacitance method, it's because the storage of heat actually is the analog of a capacitor. And the key thing here is assume temperature inside is uniform. All right, so if I doing lumped capacitance, how do these two temperatures on two different parts of the surface compare? The same. Better be the same, right? I'm not trying to be tricky. It's that very, very often after we all agree on something, then you start having doubts when you do the either problems at home or the exam. It's as easy as saying everything is the same and we mean damn the same. Not in time. In time things are going to change, but not in space. Right? Before we saw how it changed in space, but not in time. And in a couple of weeks, we're going to see how we change both space and time.